Hello, my name is Patricia Rose De Leon, and today I will be doing the fifth Think Aloud assignment for the class Introduction to Human Physiology. So, I believe the topic for this chapter would be about the generation of action potentials. So, as noted by our instructor, Professor Lee, I will only be doing the generation of action potentials section. So, I won't be going over the graded potentials and the propagation of action potentials. And just a quick note before I start reading. Um, so when I read, I will go. When I read, I will go in the order from left to right, just so when you guys watch this video and want to follow along when I'm reading, you can see the order that I'm going to, and there's no confusion when when I start reading the text. So yeah, since I have a lot to go through today, I will just get started. Okay, so generation of action potentials. An action potential, or AP, or impulse, is a sequence of rapidly occurring events that decrease and reverse the membrane potential and then eventually restore it to the resting state. An action potential has two main phases, a depolarizing phase and a repolarizing phase. Figure 12.18. We'll look over that later, but let's just finish reading this paragraph first. So during the repolarizing phase, the negative membrane potential becomes less negative, reaches zero, and then becomes positive. During the repolarizing phase, the membrane potential is restored to the resting state of negative 7 millivolts. Following the repolarizing phase, there may be an after hyperpolarizing phase, during which the membrane potential temporarily becomes more negative than the resting level. Two types of voltage-gated channels open and then close during an action potential. These channels are present mainly in the axon plasma membrane and axon terminals. The first channels that open, the voltage the voltage-gated sodium channels allow sodium to rush into the cell, which causes the depolarizing phase. Then voltage-gated potassium channels open, allowing potassium to flow out, which produces the repolarizing phase. The after hypolarizing phase occurs when the voltage-gated potassium channels remain open after the repolarizing phase ends. Okay, so right off the bat, I do know what I also I already know what an action potential or an impulse is, as well as what the depolarizing phase and the repolarizing phase is, because um if you guys didn't know, I've mentioned in my previous videos, but that I took AP psychology during my junior year in high school, and um there was a biological unit in AP psychology where we talk about neuroscience, and yeah, it went over topics such as action potential threshold, um, parts of the neurons and stuff like that. So yeah, I think it's a really it's really great to know um, these information beforehand, because it'll help you kind of process and analyze the text as you go forward in reading them. So I believe, in my interpretation and from what I actually remember from my AP psychology class, is that the action potential or the impulse is kind of like this explosion of like electrical activity that is created by the depolarizing current. So this means that some event or like a stimulus, it causes like the resting potential to move towards like a zero that moves towards 0 millivolts. And when depolarization reaches about, let's say, negative 55 millivolts, and that will cause a neuron to fire like an action potential. So yeah. Okay, so basically depolarization or the depolarizing phase is, I believe, is this movement of the cell's membrane potential to like a more positive value. So that means like the inner membrane it becomes less negative. It also increases like the membrane potential, and then it's also something that facilitates the firing of an action potential. And as mentioned in the end of this paragraph, it is caused by the opening of the sodium channels, and it kind of like so in that way I believe it kind of results in like it acts like a stimulating effector. So it results is like a stimulating effector, such as like the muscular contractions. But on the other hand, the repolarizing phase or repolarization is like this change in the membrane potential, which returns to like its negative value. So, compared to the depolarizing phase where the inner membranes becomes less negative, um, in the repolarizing phase, it turns the inner membrane negative, and in and it also decreases like the membrane potential, and which means it restores like the resting membrane potential. And I also do remember in my AP psychology class that the repolarization phase is what's preventing the firing of like an action potential. And just to connect it back to the how depolarization is caused by like the opening of sodium channels, and on the other hand, repolarization is caused by the closing of like the sodium channels and the opening of the potassium channels, as mentioned in this section. So yeah, moving on. An action potential occurs in the membrane of the axon of a neuron when depolarization reaches a certain level termed the threshold. So yeah, I did mention that I knew about the threshold. So let's just keep going, which is about negative 55 millivolts in many neurons. Different neurons may have different thresholds for generation of an action potential, but the threshold in a particular neuron it usually is constant. The generation of an action potential depends on whether a particular stimulus is able to bring the membrane potential to threshold. Figure 12.19. An action potential will not occur in response to a subthreshold stimulus, which is a stimulus that is a weak depolarization. Okay. So basically, I'm very sorry for like the long pause. I had to step out for a quick second, but okay, let's just continue. So from how I interpret this is basically the threshold potential is kind of like this critical level in which like the membrane potential it must be like depolarized to initiate like an action potential. So connecting it back to the whole biological aspect, and I believe in that way threshold potentials they're necessary because they're used to kind of like regulate and propagate like signaling in both the central nervous system and the peripheral nervous system. So a subthreshold stimulus which This is actually the first time I've ever heard of it. Um, as I said before, we didn't really go over the neuroscience aspect of psychology on a greater context. But so, from how I interpreted the meaning given by the text, is that basically the subthreshold stimulus is something that, so basically it's kind of like a stimulus that is too small in magnitude to kind of produce an action potential. So if it's too small, then it probably leads to like depolarization of the membrane. But I think like the magnitude of the depolarization is not that large, it's not that big, and it's not that big enough to reach like a threshold voltage. So yeah. Okay, so figure 12.18, which was mentioned here in the earlier paragraphs. So, an action potential, a pure impulse. When a stimulus depolarizes the membrane to threshold -55 millivolts, an AP is generated. The action potential arises at the trigger zone, here at the junction of the axon hillock and the initial segment, and then propagates along the axon to the axon terminals. The green-colored regions of neuron indicate parts that typically have voltage-gated sodium and potassium channels, axon plasma membrane, and axon terminals. So green color regions of the neurons, voltage-gated. Okay. An action potential consists of a depolarizing phase and a repolarizing phase, which may be followed by an after hyperpolarizing phase. So yeah, it was mentioned before in the earlier paragraph. So let's look over this graph on the left. So this is the resting membrane potential. Voltage gated sodium channels are in the resting state, and voltage gated potassium channels are closed. Stimulus causes depolarization to threshold. Okay, stimulus causes depolarization to threshold, and then voltage gated voltage gated sodium channels activation gates are open, and then the voltage gated potassium channels are open and the sodium channels are inactivating. Which is the absolute refractory period. Okay, so during these part, during this part, it is the absolute refractory period, basically meaning that the green is the depolarizing phase, which basically means the voltage gated sodium channels, they're open, and in the repolarizing phase, the sodium channels close and the potassium channels open. So if this is the absolute refractory period, then this should be the relative refractory period, in which the voltage gated potassium channels are still open, but the sodium channels are in a resting state. Okay. Stimulus. Okay. So yeah, got this. Pretty the graph and the key here is pretty self-explanatory. So yeah, let's just move on. So which channels are open during the depolarizing phase, during the repolarizing phase? Okay, so I'll answer this first question first. So which channels are open during the depolarizing phase? And it's mentioned here in the key, but basically after so yeah, following depolarization, the voltage-gated sodium ion channels, they're open, and while the cell was like undergoing depolarization, close again. So yeah, it's because like the increased positive charge within the cell now causes like the potassium channels to open. So yeah, during the depolarizing phase, the voltage gated sodium ion channels open. So during the repolarizing phase, basically the sodium ion channels closes and the potassium ion channels open, as mentioned here in the key. Okay, so moving on, figure 12.19, which was about threshold and the subthreshold stimulus. So stimulus strength and action potential generation. A subthreshold stimulus does not cause an action potential because it does not bring the membrane potential to threshold. However, an action potential does occur in response to threshold stimulus, because a threshold stimulus is just as strong enough to depolarize the membrane to threshold. Several action potentials form in response to a supra-threshold stimulus, which depolarizes the membrane above threshold. Each of the action potentials caused by the supra-threshold stimulus has the same amplitude size as the action potential caused by the threshold stimulus. For simplicity, the after hyperpolarizing phase of the action potential is not shown. So an action potential will not only occur once the membrane potential reaches threshold. So yeah, basically, threshold stimulus is this minimum stimulus that is like needed to achieve an action potential. And as mentioned, the threshold stimulus causes like the membrane potential to become less negative, and because like a stimulus, like no matter how small it is, it causes like a few sodium channels to open, and it allows like some positively charged sodium ions to diffuse in. So, looking at this graph, let's see. So, as the stimulus strength increases, as time in milliseconds increases, the stimulus strength also increases. That's the membrane potential, threshold. Okay. So I'm a bit confused as to what these values mean, the membrane potential, and how I can interpret it to the graph, but I might have to look that up later on. Okay. So will an action potential occur in response to a hyperpolarizing graded potential that spreads from the dendrites or cell body to the trigger zone of the axon of a neuron? Why or why not? Okay, so before I actually answer this question, let me just go over the definition of graded potential that was given here at the first section. I know I'm not supposed to read this part, but I might as well try. The graded nature of graded potentials as stimulus increases, the amplitude size of each resulting depolarizing graded potential increases. Although not shown, a similar relationship exists between the stimulus strength and the amplitude of a hyperpolarizing graded potential. Summation of graded potentials. Summation of two depolarizing graded potentials happen in response to two stimuli of the same strength that occur very close together in time. The dotted lines represent the individual depolarizing graded potentials that will form if summation did not occur. Summation occurs when two or more graded potentials add together to become larger in amplitude. Okay, so the question is, will an action potential occur in response to a hyperpolarizing graded potential that spreads from dendrites or cell body to trigger the zone on the axon of a neuron? Why or why not? Um, I don't think an action potential I don't think it will occur because, as mentioned, the hyperpolarizing graded potential causes like the membrane potential to become um to become more negative in the inside. So therefore, it will be like more farther away from from the threshold, which is like negative 55 millivolts. So yeah, I don't think an action potential will occur. Okay, so where did we left off? An action potential will not occur in response to a subthreshold stimulus, a stimulus that is weak, depolarization, that cannot bring the membrane potential to a threshold. However, an action potential will occur in response to a threshold stimulus. A threshold stimulus is just strong enough to depolarize the membrane to threshold. Several action potentials will form in response to a supra-threshold stimulus, a stimulus that is strong enough to depolarize the membrane above threshold. Each of the action potentials caused by the supra-threshold stimulus has the same amplitude size as an action potential caused by a threshold stimulus. Therefore, once an action potential is generated, the amplitude of an action potential is always the same and does not depend on stimulus intensity. Instead, the greater the stimulus strength above threshold, the greater the frequency of action potentials until a maximum frequency is reached as determined by the absolute refractory period described shortly. So, so it is actually in this part they mention the meaning of the threshold stimulus as well as the supra threshold stimulus. So when I was reading this part, I didn't actually understand what they were mentioning or what they were referring to. So once I go over this text, I will probably go back to this figure 12.19 and then analyze this section once again. So it will make more sense. So yeah, threshold stimulus is just this like minimum stimulus that is like needed to achieve an action potential. And the supra threshold stimulus, so basically it's like the stimulus that is like large enough in magnitude to produce an action potential. So and basically the absolute refractory period is from how I interpret it in this text is basically is this kind of I think it's a brief interval after like a successful stimulus. How do I explain this? So I think um absolute refractory period is like when there's like no amount of depolarization current that can cause like an action potential. Okay, so moving on. As you have just learned, an action potential is generated in response to a threshold stimulus but does not form a when there is a sub-threshold stimulus. In other words, an action potential either occurs completely or it does not occur at all. This characteristic of an action potential is known as the all or none principle. The all or none principle of the action potential is similar to pushing the first domino in a long row of standing dominoes. When the push on the first domino is strong enough, when the depolarization reaches threshold, the domino falls against the second domino and the entire row topples, and action potential occurs. Stronger pushes on the first domino produce the identical effect, toppling off the entire row. Thus, thus, thus pushing on, thus pushing on the first domino that produces an all or none event. The dominoes all fall or none fall at all. So yeah, I did learn about this all or none principle in my AP psychology class, and yeah, it's basically how I remember it. And I think it's this like principle, like that the amplitude of the action potential in a neuron is independent of the magnitude of a stimulus. So yeah. Okay, moving on to depolarizing phase. So when a depolarizing gradient potential or some other stimulus causes the membrane of the axon to depolarize to threshold, voltage-gated sodium channels open rapidly. Both the electrical and the chemical gradients favor inward movement of sodium, and the resulting inrush of sodium causes the depolarizing phase of the action potential. See figure 12.18. Okay, right here. The inflow of sodium changes the membrane potential from negative 55 millivolts to positive 30 millivolts. At the peak of the action potential, the inside of the membrane is 30 millivolts, more positive than the outside. So yeah, as like mentioned before, the depolarization occurs when like the stimulus reaches like a resting neuron. So I think basically what it's trying to say is that during the depolarization phase, the gated sodium ion channels on the neuron's membrane, they suddenly like open and allow all of these sodium ions present outside of like the membrane to rush into the cell. And as like a result, the inner portion of the cell reaches like um positive 40 millivolts. Okay, so each voltage gated sodium channel has two separate gates, an activation gate and an inactivation gate. In the resting state of a voltage gated sodium channel, the inactivation gate is open, but the activation gate is closed. Step 1 in figure 12.20. Okay, so this is the resting state. So this is the sodium channel and it's open and the okay. Activation gate closed. Oh, yeah, there's two gates. So this is the activation gate and this is the inactivation gate. So basically, resting state, activation gate closed, and activation gate open. As a result, the sodium cannot move into the cell through these channels. At threshold, voltage-gated sodium channels are activated. In the activated state of the voltage-gated sodium channel, both the activation and the inactivation gates in the channel are open, and sodium inflow begins. Step 2 in figure 12.20. As more channels open, sodium inflow increases. The membrane depolarizes further, and more sodium channels open. This is an example of a positive feedback mechanism. During the few 10,000ths of a second that the voltage-gated sodium channel is open, about 20,000 sodium flow across the membrane and change the membrane potential considerably. But the concentration of sodium hardly changes because of the millions of sodium present in the extracellular fluid. The sodium potassium pumps easily bail out the 20,000 or so sodium that enter the cell during a single action potential and maintain the low concentration of sodium inside the cell. So basically during the activation state, or also like the process of opening the activation gate, um so basically this occurs in like in response to like the voltage inside like the cell membrane, the membrane potential, and they become more like positive like with respect to like the outside of the cell, which is like depolarization. And yeah, so functionally during depolarization, the channel has like two gates as mentioned, which is like the activation gate and the inactivation gate, and both and I think both of which must be open for the conduction to occur. So the channel's activation gate is closed at rest, and it activates in like several steps, as mentioned here in the figure 12.20, to an open state after depolarization. And on the other hand, the activation gate is open at rest and it closes relatively slow after depolarization in a single step, as you can see here in figure 12.20. I'll go over it a bit later and more in depth, but yeah. Okay. So moving on to the repolarizing phase. Shortly after the activation gates of the voltage-gated sodium channels open, the inactivation gates close. Step 3 in figure 12.20. Now the voltage-gated sodium channels is in inactivated state. In addition to opening voltage-gated sodium channels, a threshold level depolarization also opens voltage-gated potassium channels. Steps 3 and 4 in figure 12.20. Because the voltage-gated potassium channels open more slowly, their opening occurs at about the same time the voltage-gated sodium channels are closing. The slower opening of the voltage-gated potassium channels and the closing of previously open voltage sodium channels produce the repolarizing phase of the action potential. As the um, as the sodium channels are inactivated, sodium inflow in I assume that's inflow slows. At the same time, the potassium channels are opening, acceler- accelerating, accelerate, accelerating potassium outflow. Slowing of sodium inflow and acceleration of potassium outflow causes the membrane potential to change from positive 30 millivolts to negative 70 millivolts. Repolarization also allows inactivated sodium channels to revert to the resting state. So I'll go look at step 3 and 4 in figure 12.20 before I move on to after hypo, hyperpolarizing phase. So on step 3, repolarizing phase begins. Sodium channel activation gates close and the potassium channels open. Membrane starts to become repolarized as some potassium channels leave neuron and few negative charges begin to build up along inside the surface of the membrane. Okay, the potassium channels open. So you can see here the Na channel is closed, the sodium channel is closed. I assume these triangles are the potassium ions and they leave to the potassium channel. Okay, so fourth step is the repolarization phase continues. As As potassium outflow continues, as more potassium ions leave neuron, more negative charges build up along inside the surface of membrane. Potassium outflow eventually restores resting membrane potential. Sodium channel inactivation gates open. Returning to the resting state occurs when potassium gates close. So it reverts back after the repolarization phase, it reverts back to the resting phase. So after hyperpolarizing phase, while the voltage-gated potassium channels are open, outflow of potassium may. Okay, so I can't clearly read this side here, but I'll try to assume what it's trying to say. Outflow of potassium may be large enough to cause an after hyperpolarizing phase of the action potential. See figure 12.18. During this phase, the voltage-gated potassium channels remain open and the membrane potential comes even more negative, about negative 19 millivolts. As the voltage-gated potassium channels close, the membrane potential returns to the resting level of negative 70 millivolts. Unlike voltage gated sodium channels, most voltage gated potassium channels do not exhibit an inactivated state. Instead, they alternate between closed resting, and open activated states. So let's look at figure 12.18 first. So it's probably referring to this phase where the voltage gated potassium channels are still open, but the sodium channels are in the resting phase. So yeah, as mentioned here, unlike voltage gated sodium channels, most of the potassium channels do not exhibit an inactivated state because it's in the sodium channels are in resting state. So refractory period. The period of time after an action potential begins during which an excitable cell cannot generate another action potential is response to a normal threshold stimulus is called the refractory period. See key in figure 12.18. During the absolute refractory period, even a very strong stimulus um, can initiate a second action potential. This period coincides with the period of sodium channel activation and inactivation. Steps 2 and 4 in figure 12.20. Inactivated sodium channels cannot reopen. They must return to the resting state. Step 1 in figure 12.20. In contrary, in um, I'm not sure what that word is, but to action potentials, graded potentials do not exhibit a refractory period. So yeah, as I mentioned before, um, the absolute refractory period is basically this period in which is during which like a cell is incapable actually during like a cell is incapable of repeating like an action potential, and during a absolute refractory period it's this kind of like interval of time during which like a second action potential cannot be initiated, like no matter how large a stimulus is like repeatedly applied. Okay, so a large diameter axons have a larger surface area and have a brief absolute refractory period of about zero point 0.4 milliseconds because a okay I I don't know what this is. The word is kind of blurred, but nerve impulse can arise very quickly, up to 1,000 impulses. Second are possible. Small diameter axons have absolute refractory periods as long as 4 milliseconds, enabling them to transmit a minimum of 250 impulses per second. Under normal body conditions, the maximum frequency of nerve impulses in different ranges between 10 and 1,000 per second. So basically, large diameter axons are um how do I say this? They have this like higher conduction velocity, which means they're able to send signals faster. As you can see here, it says it has a refractory period of about 0 point millisecond. And I think it's because there is like less resistance when facing the ion flow. So the relative refractory period is the period of time which a second action potential can be initiated, but only when the larger than normal stimulus. It coincides with the period. Okay, so I've looked over figure 12.20 already, and I think I kind of get the steps here from the resting phase, the depolarizing phase, the repolarizing phase, and the repolarization phase. I think actually I guess I can answer this question. So given the existence of leak channels for both potassium and sodium, could the membrane repolarize if the voltage gated potassium channels did not exist? Um so the answer to this question is I think it would be probably yes, because as mentioned, like the lead channels would still allow the potassium to exit more rapidly than sodium could enter the axon. So yeah. So and yeah, if I remember, it was mentioned in previous text that like some mammalian like myelinated axons only have like a few voltage gated um, potassium channels. So it coincides with the period with the voltage gated potassium channels are still open after inactivated sodium channels are returned to their resting state. Figure 12.18. So yeah, as you can see here, it returns to resting state and then repeats the kind of cycle again. Okay, so that ends the think aloud assignment for chapter 5. I don't have to read the propagation of action potentials and the graded potentials as instructed by Professor Lee, but um, if needed, I think if it's if this text and the information here is needed, then I would probably read it over quickly just so I'm prepared for like future assignments and homeworks. But so yeah, I think that concludes um, the fifth reading aloud assignment for the class Introduction to Human Physiology. I hope to whoever is watching this enjoyed, you know, going over the text with me, and I hope that you learn as much as I did. Um, so yeah. Um, Also, I think if this video is too if it's too long, if it's over, I believe, an hour, then it won't be able to upload to Canvas. So what I will do is I will send a Google Drive link of the video to the comment section when you do the submission, because in Canvas you can put a comment with your submission, and you can view that video in that way. So So yeah, thank you so much for listening to my Think Aloud, for my fifth Think Aloud assignment, and I hope you learned. I hope you, I hope you learned, and I hope I did learn a lot about the action potentials, the generation of action potentials, and yeah, thank you so much for listening, and have a nice day.